Today I'm going to talk about some of our work in using emerging memory technologies to accelerate important classes of workloads, including some from the domain of combinatorial optimization and machine learning. With the emergence of resistive memory technologies such as SRAM, such as STT-MRAM, phase change memory, and RRAM, the spectrum of devices that are now available to a computer architect to design memory systems has enormously increased over the last 10 years. These technologies are initially being pursued as replacements for today's SRAM, DRAM, and flash-based, charge-based memory systems. But beyond that, they also offer some unique capabilities to do computation in fundamentally different and new ways. As a computer architect, when I look at this current state of affairs, I see that there are two different paths that one can follow. One thing that we could do would be to say, hey, maybe I can look at these devices and try to understand how I can fit within the existing paradigm, how I can change the technology, but not necessarily the architecture in a significant way within the existing memory hierarchy, and see what I can get from that. And we've done a bunch of work in this area as well. So, for example, you can imagine replacing, you can imagine, for example, replacing your DRAM with byte addressable persistent memory, which then blurs the distinction between storage and memory and results in much faster I/O performance than is otherwise available on today's devices. You can take a step forward, and you can say, hey, actually, we can maybe replace the SRAM, which we today use to implement the last level caches, with STT-MRAM. And the minute you do that, you get some benefits as well, because the technology is denser, the footprint of the cache shrinks. Now the wires are shorter, the data movement energy is substantially reduced, and also because the technology is non-volatile, your standby power, your leakage power is significantly lower as well. You can also take one more step, and you can say, hey, maybe I can push these technologies deep into the micro-architecture of an out-of-order core. And when you do that, a lot of the structures that we use that are performance critical, like load store queues, register files, rename maps, reorder buffers, and so on, actually become better in the sense that within a fixed cycle budget, you now are able to have much more capacity because the technology is denser, so you can exploit instruction-level parallelism much more aggressively. All of these would be examples of fitting within the existing paradigm with these new technologies. But there's something else that you can do, which is actually much different. And that is to say, hey, these devices, in addition to being memory devices, being storage media, they also have some interesting electrical properties that may allow us to do computation in fundamentally different ways, perhaps in the analog domain, perhaps in a stochastic way. And if we build accelerators that can cater to the needs of important classes of workloads using these, that will be an accelerator that's using unconventional technologies, very different from how we do things today. But maybe by using these unconventional technologies, maybe we can get unconventional benefits as well. And if we do that, it's important that we would want to put those accelerators behind interfaces that are very well defined, like DRAM or PCI, such that we can selectively include them in systems that benefit from that, because these accelerators are not necessarily going to help every possible workload. So today I'll talk about two of the pieces of work that we did in this area, one of them for accelerating a particular model called the Boltzmann Machine, which is used in combinatorial optimization, and another for sparse linear solvers. Okay, so I'll start with the Boltzmann Machine. And what the Boltzmann Machine is it's essentially a method of performing combinatorial optimization. Combinatorial optimization itself is a branch of discrete mathematics that is concerned with finding the optimum element of either a finite or countably infinite set. And the reason it's important is because there's an enormous number of problems in science and engineering that can be cast within the combinatorial optimization framework. Some of these are classical things like traveling salesman and knapsack and bin packing, but even in machine learning, during the training phase, oftentimes what we end up doing is we define a well-defined family of models, and then the training phase essentially boils down to identifying or quickly narrowing down on the actual parameters that optimize a particular error rate on that model, which comes out of an optimization procedure. Many of these problems in practice end up being intractable, and as a result, we end up using heuristic algorithms for solving them. Among these, one of the oldest and still successful ones is the simulated annealing method. But the simulated annealing actually suffers from limited parallelism. And as a result, in the 1980s, this bottleneck was addressed by using a massively parallel instantiation or version of simulated annealing called the Boltzmann machine. In recent years, this has received much more interest in the research literature because it's one of the more successful methods of performing unsupervised initialization or training of certain classes of deep neural network models. So let's quickly go over the Boltzmann machine and what it actually is. It's an abstract model. It's a fully connected, undirected graph with weighted edges. And every node within this graph has binary states. It's either in a 0 state or a 1 state. And what we are trying to do is we are trying to find a setting of these weights, or rather setting of these states, such that we minimize a particular parameter called the network energy. To understand what the network energy is, it's important to first understand what an active versus inactive edge is in this graph. We say that an edge is active when both of the nodes that are incident to it are in the 1 state. If at least one of them is in the 0 state, we're going to say that that edge is inactive. And what we're going to do is we're going to simply sum all of the edge weights associated with all of the active edges in this network and multiply by -1 to turn it into a minimization problem. Yeah, the edges are those lines. That's right. The edges are the lines in the model. During the optimization procedure, every single node within this graph is going to decide how to change its state independently and in parallel with every other node. It's going to happen asynchronously. And the way it's going to do that is it's going to ask itself a simple question. It's going to say, hey, if I were to change my state from a 0 to a 1 at this particular point in time, how much would the total network energy change, assuming nothing else changes in the network? And based on that delta energy change, it is going to probabilistically sample from the Boltzmann distribution to determine whether we should switch to the next state or whether we should stay put. Okay, so here is an example to illustrate this concept. In this particular case, we have 4, or rather 3 active edges, and the total network energy is 4. After a while, one of the nodes in the network decides to go into the 0 state as a result of this optimization procedure, and then the network energy is now lower, and it's equal to -1. So this by itself is an abstract model. It's only useful to the extent that you can take a problem that you actually care about and are able to map it to this formalism, and then we have algorithms that make this computation, this optimization succeed. And in general, the way a given combinatorial optimization has been mapped onto the Boltzmann machine has been application specific in the past. I just picked one particular example that's rather simple to explain in a couple of minutes. And this is the problem of maximum cut, where it's a classical problem where we're given an undirected graph, and our job is to partition this graph into 2 subgraphs such that the sum of the edge weights for those edges that go from one subgraph to the other is maximized. So we're going to try to find a cut whose total edge weight is maximum. To do this, the first thing that you have to do is to find an instantiation of the Boltzmann machine, and for maximum cut, this ends up being rather simple. It's identical topologically to the graphical model that you started with. Then there is an initialization of the edges, in this case by multiplying the original edges by -2. And then we randomly initialize the states and simply let the network perform its optimization over various different iterations. When the network states converge and they settle, we interpret the results by saying that all of those units that are in the 0 state correspond to one particular subgraph, and all of those that are in the 0 state correspond to another subgraph. Okay, so that's a brief overview of what the Boltzmann machine is. As a computer architect, when I look at it, the question that I ask myself is, what is it actually doing? That computationally, where is the core of this model that needs to be attended to? And essentially it's doing iterative matrix vector multiplication between the weights and states repeatedly for every single unit in this model. In fact, this will be sort of, I believe, a repeated theme in any other talk that you hear on connectionist models, that matrix vector multiplication is going to play a critical role. Because this takes a long time, because it's fully connected and the storage requirements may be rather large. In the past, people have tried to accelerate this. There have been FPGA-based solutions. There have been solutions on GPUs, solutions on ASICs that have tried to minimize data movement, and at the end of the, or rather improve performance. But at the end of the day, the problem always comes to the fact that you end up moving a lot of data from your memory arrays into your customized functional units, which you have either designed on an FPGA or an ASIC or in some other way. But unless you eliminate this data movement, it quickly becomes your bottleneck in terms of your energy. It becomes a bottleneck in terms of your throughput. So we wanted to address that. We wanted to, rather than design yet another functional unit or customized execution engine, we wanted to actually do computation in situ within the memory cells themselves. In other words, we wanted to compute in the analog domain, and when we access one of these arrays, what we want to read out is not one of the operands. We want to actually read out the result of the matrix vector multiplication directly in the analog domain from the Memristive arrays. Here is how we propose to do this. We rely on resistive random access memory. At a very high level, an RRAM cell comprises one access transistor and the resistive switching medium, which is connected to a bit line and a word line as shown in this picture. When you want to do a read, you simply activate the corresponding word line and measure the bit line current that you are driving. It's also possible to connect multiple such cells in parallel to the bit line and turn them all on at the same time. And then just by using simple current summation by looking at KCL, you can tell that the sum of the individual bit line currents that you are pulling is going to be proportional to the individual conductances of these Memristive devices. This gives us an ability to actually map the computation that the Boltzmann machine is trying to perform in the analog domain to a resistive bit line. If we program the resistors, or the memristors in this case, in inverse proportion to the weights, and then control the bit line and word line voltages by using the state variables, then the current that we draw is going to be proportional to the energy change that we are essentially proposing. Now this seems fine. This seems like old analog computing from many, many years ago coming back, but there are some issues. It's not as simple. One of the issues that comes up is how you represent data. It turns out that for the particular optimization problems that we will look at, for some of them, going from even 16 bits to 32 bits actually makes a big difference. And we do not believe that Memristive RRAM devices will be offering us 32 bits of precision anytime in the near future. We don't want to count on that. We don't want to put a bet on technology in that particular way. So what we're doing is we're taking a single weight, which could be 32 bits, and we're spreading it across many, many cells that are connected to the same word line. Because the final operation that we're trying to perform is linear, right? It's matrix vector multiplication, and linearity has this beautiful advantage that you can always spread your computation, and then in the end you can put things together and everything still makes sense. So we're going to try to do that. We're going to spread a single weight across multiple bit planes, as we call them. Now we're going to augment this array with peripheral circuitry so that we can hold our state variables. We don't want to be writing state variables into RRAM. We want to be writing them into static CMOS latches. And then we're going to augment this array with A to D converters so that we can read and shift out the results of the actual computation. We have a need to keep these A to D converters simple. Pretty much everybody who has since then tried to apply analog computing to these kinds of, or at least this array-based computing to matrix vector multiplication has found that the technology is great, RRAM is dense, or some people use other technologies, and you end up with a tiny array and an enormous A to D converter that swamps all the area benefits that you came up with, unless you're very careful in imposing requirements on that ADC. In our case, we have a simple 5-bit ADC, which means that we can only sense 32 word lines at a time. So we're going to essentially stage this thing over multiple cycles. We are going to do a 5-bit sensing operation over 32 word lines, and then move on to the next word line, and so on and so forth. We're going to generate these partial sums. We're then going to pad them appropriately with zeros to align their significance positions. And then we're going to essentially do bit serial addition along the bottom periphery of this picture, such that what we shift out of the chip is a single bit stream that corresponds to the result. Rather than having to route around a large set of wires, we're just going to route the bit stream. This is just a single array. We actually have a hierarchical chip organization in which multiple mats and subbanks are connected into a bank, and the reduction tree merges multiple bit streams that are coming from various different banks. Then a controller essentially calculates the final result, performs the nonlinear activation function, in this case sampling from the Boltzmann distribution, and then goes on to perform another round of iterations. Then there's the question of how this thing fits into an actual system. We chose to integrate it onto the DRAM bus. It could have been integrated into others. Others choose PCI Express. DRAM gives us better latency, faster communication. And the basic idea is that we configure the DIMM by writing to an on-DIMM controller. This DIMM is, in fact, DDR3 compatible. Yeah, so this is a dual inline memory module. This essentially plugs into your motherboard, and your memory controller accepts it as a DDR3 module. You don't need extra hardware other than this on your motherboard. You write the weights and states, you compute, and then you poll for readiness. You read when the result is done. We sort of made a comparison. I won't go through, bore you with the details, but the important thing to notice is we went to each and every single one of the particular applications that we looked at, and in the optimization community, whatever is considered the state of the art for that particular application, we ported it to a CPU. So we use semi-definite programming for MaxCut, a program called MaxVolksat for MaxSat, a deep leaf network application. And we created software kernels for these. We also took the original Boltzmann machine and generated both single and multi-threaded software implementations of this to compare against our design. But the truth is, none of these are actually strong baselines. A real strong baseline, if you're doing analog computing with RRAM, the real strong baseline is something that looks like this. So this is processing in memory. PIM, it's been around, it was invented earlier than my birth, right? This is like 40 years old. Putting small digital logic gates right next to small arrays and doing computation within memory is not a new idea. This is well known. RRAM is not our invention. So if you're getting benefits because of RRAM's density, then that's great, but that's not necessarily a contribution. So if you told me that you had access to RRAM, I would say, hey, let's just do, if you want to eliminate data movement, let's just do a PIM using RRAM arrays and conventional CMOS gates. Huh? But that's processing in memory. Okay? Just think of it as small amounts of computational units right next to individual memory arrays in a memory chip. Okay, so whatever analog computation, whatever the benefits of analog computation are, it has to be compared to this, because this is the right baseline. Stuff running on a CPU or GPU is simply not the right baseline. So here's the results that we got. This is a plot that shows on the y-axis energy and on the x-axis execution time. And when you compare, this is the maximum cut problem. So when you compare against software, you get about 38x benefits on the time axis and 16x on the energy. And when you compare to the PIM implementation, you get about 4x and 5x in either of these dimensions that you care about. Similar results on maximum SAT, and similar results on deep learning. So maybe about 2 orders of magnitude over software, and maybe up to an order of magnitude on hardware. Okay, so far so good. We can now quickly figure out what else we can do with this. The truth is, what we have actually done is we have simply accelerated linear algebra. Okay? And now the question we might ask ourselves is, deep learning is great and machine learning is wonderful, but what else can we do with linear algebra? And the answer is we can do a lot with linear algebra, because linear algebra is everywhere, right? Linear algebra is at the heart of science and engineering. We take partial differential equations, discretize them, which results in large systems of linear equations, solve them on supercomputer clusters. This actually requires 128 bits of precision. How can we get any benefits in this kind of setup? And we have actually developed an approach to iterative linear solvers. I'm running out of time, so I'll just quickly summarize what this is. It turns out that using a resistive mesh, we can come up with an approximate analog solver that gives us precision nowhere near what today's digital solvers provide you. But that's okay, because what we end up doing is we notice that today's solvers are all iterative solvers. In other words, they try to guess the solution, and then they iteratively improve upon that solution over a series of steps. Things like conjugate gradient do that, for example. So what we're doing is we're taking this analog accelerator, which we are using to quickly query to achieve a very fast and somewhat accurate seed. We're passing it onto a digital machine and computing the rest of the iterations on this digital processor. The end result is that we just skipped over a whole bunch of iterations and we're faster, but the end result is just as accurate as purely digital. I guess I don't want to run out of time. The results of this are actually quite about 1500x speed up compared to a GPU. Then we run what is referred to as HPCG on this GPU. And the final thing that I would like to say is that Memristive have potential beyond the memory hierarchy. They are great for designing memories, but actually by using the physical properties of these devices, it is possible to deliver speed-ups to important classes of workloads like optimization, simulation, modeling, and machine learning. Thank you.
So that was the first talk that used the analog word, okay? And so we heard from Amir previously that the precision requirements are not that great. And if so, maybe I guess what you told us, analog can deal with that and can provide tremendous benefits. So let me call for questions. Let's give someone else a chance. Okay.
Great talk. Yes, precisely mentioned the word about analog. So my question is about this analog to digital conversion. So I have been looking into the current existing ADC converters. Like one of the big challenge for this is we probably need a big array of ADCs, maybe hundreds or even thousands of ADC arrays. And I looked into it right now on the market, no one have built like fast ADC arrays for more than 16 channels, for example. And if you want high speed, even 8-bit precisions, not like hundreds of channels ADC haven't been built yet. So but in order to use analog, you need this. So how do you comment on this?
Right. So this is all integrated on the chip. So we designed our own 5-bit flash ADC, and it's actually published in a separate conference, not the paper that I am showing here. The ADC does not need to be very aggressive simply because we're trying to sense only 32 word lines at a time. I will say one more thing about the ADC. We have an upcoming TVLSI paper on this. One of the biggest components in the ADC ends up being the DAC. So every ADC has this internal DAC, oftentimes implemented using a capacitive DAC, because the ratio between capacitors is one of the things that's reasonably controlled in the LSI design. The DAC ends up using a lot of area because of that. If you have these kinds of devices, Memristive devices, which you can program to, let's say, within 1% precision, if you take your time in writing, which you can calibrate. Then you can design an ADC that instead of a capacitive DAC, uses an R2R ladder from high school. And because the devices are so much smaller than capacitive DACs, your area shrinks by about 8x. We haven't done that here, but it's a promising area that people are looking into, that these devices can also help ADC design itself.
Okay, now one-part question.
Okay, yeah. Just one question. So, there is a lot of talk about in-memory, I call it, before sense-amp computing, right? You are doing stuff before the sense-amp and then collecting the results. And, there are lots of projections about how, that would give big energy efficiency benefits. But realistically, two things will happen. First of all, your array sizes will tend to be small because those are the most optimized array sizes for on-chip implementations. And second, realistically, you would have a mix of situations where sometimes you're computing, doing this kind of in-memory computing, and sometimes you're simply going to use those memories for lookups because, in a general architecture. So do you have any comments on, what is really the benefit of this pre-SenSamp, before SenSamp computing, if you consider all those situations together, or is there any benefit?
Right. So the thing that I should clarify is that we're not advocating a dual use for this system. This is not trying to do, let's do Boltzmann computation on top of your existing memory. That's not what we're doing. We're saying let's just design a customized Boltzmann machine accelerator. That's all that it's good for. We're not trying to see how we can efficiently do this computation and be a memory at the same time.
No, you promised a one-part question. Okay, so here's my suggestion. We're about to break for lunch. You're holding up everybody's lunch. Let's ask that question at lunch. The other thing I want to mention is we have another talk on the analog matrix multiplication and neural networks coming up this afternoon from Dr. Agarwal from Sandia Labs. So with that, let's thank Professor Ipek.